Okay, welcome back again. So if you recall, in my yesterday's class, so I was dealing with vector equation of straight line, vector equation of a plan, right? And over there, I just made one mistake, like say it was kind of writing error. So if you recall, I mean, if you want to find out the vector equation of a plan passing through a point, fixed point, this, okay, and on the plan, if you consider a normal having component A, B, C, so then eventually it turns out that the vector equation of the plan is this y minus y naught, that's C, j minus z naught equal to 0. And then what I did, I simplified it into, I told you, okay, but over there, I had written this j as y. Please correct it. Probably you would have noticed it. Okay, so please correct this as j as y. Okay, so I mean, what I mean to say is that whenever you see the equation of a plan in this form, you should immediately be able to recognize that A, B, and C, they are nothing but the components of the normal to that plan. Okay, fine. So this was the correction I want to make. Okay, so now today we are going to start. The concept of your vector function, and then this is going to lead me to space curve. This is going to lead me to space curve. But what I'm going to do, I'm going to firstly, I mean, derive not firstly derive, I'm going to firstly consider the limit and continuity concept for a vector value function. Okay. And after that, I'll come to space curves. Okay. All of them are interrelated. So what is a vector function or what is a vector value function? Okay. So you know that the very big definition of a function. So what you do, you consider, I mean, two sets. You consider two sets, say suppose A and B. If to each point of A, you can uniquely correspond an element of B, right? And if we say that when you assign it through a rule, if I call that rule as f, I say that f is a function from, we say, A to B. Okay. Now, in case of vector value function, what we are going to do, we are going to consider an interval. We are going to consider an interval in the real line. Okay, first. Okay. Say, suppose that interval I on real line, say, suppose I am considering this interval A. Okay, fine. So now, what I am doing, I am trying to define some functions, not a function. Okay, some functions from the interval AB to the set of real numbers. Okay, so basically, what I am going to do, say, suppose you consider some point T belonging to AB. So then, suppose this is my real line. Okay. So now, if from here I define a function f, say I define a function f, so then I have a corresponding value here ft on real line, and suppose I define another function, say g. I define another function g, so I will have a corresponding value here, and similarly, say another one, say h, say, right? So it is going to give me a value ht here on the real line. Okay, so first of all, so now what we are going to do, so let me consider the set V3 of all, I mean 3D vectors. All 3D vectors. Okay, fine. So if I say that that vector is something like, say, R, a particular vector belonging to this set, if it is, I designate it by R, say, right? So definitely this R, it is going to have some components here. It is going to have some components here. Is it okay? Fine. So then what I'm going to do, if those three components, if I choose those components in such a way that corresponding to a value t lying in this interval, I choose those components as say ft, ht, ft, gt, and ht, right? So then what is going to happen? What is going to happen? Say here in the three-dimensional space, for each t, I will be able to define a vector r here. I will be able to define a vector r here. Is it okay? Fine? Okay?
Yes.
Okay, thanks. So basically what we have done, from this interval I, okay, I have been able to define a function to the set of all three-dimensional vectors. Okay, fine. So now you can see that the value of r depends upon the value of the argument t, right? So each of those vectors, three-dimensional vectors belonging to this, right? Say what is going to happen? Say suppose I have a point, say t0, I have a point t1, right? For t0, I have a corresponding vector here, so maybe I can define it as r0. For t1, maybe I can define another vector here as r1 and so on. Okay, so basically what I have done, say from this interval I to the set of all three-dimensional vector that which I have designated as V3, right? V3, I can define a function. Okay, and that function is called a vector function or a vector function. Is it okay? Fine. So this is about
Yes.
This is about, thank you. This is about vector functions. Okay. So basically what it does, see this is simply RT, it is simply FT, GT, AC, okay, and this in terms of the unit vectors along x, y, and z axis, I can simply write it as this. Okay, fine. So now, okay. Say for example, I may have RT defined as something like say sin t, 2 minus cos t, t. I may have something like this. So then you know that all this, so this sin t, 2 minus cos t, t, all of them are functions. So basically, if I define ft equal to sin t, gt equal to 2 minus cos t, and hc equal to t, right? So then it is something like this. Okay, fine. So now let me come to the limit. Of course, I'm going to revise all these things in slide. Limit of a vector function. Limit of a vector. Okay. So now, what is the limit of a vector function? So you will see that it is similar to whatever we have learned in single variable calculus. In your MA 101, in your first part, you studied single variable calculus. So all those concepts are going to be brought in here. Okay, fine. Say, suppose I am considering a vector variable function RT. So then I am going to call a fixed vector B as the limit of the vector variable function T. And remember, this T belongs to some interval I. t belongs to some interval I. Okay, so for a say suppose this is the interval I. Generally, I consider it as some closed interval AB. Okay, say suppose there is a fixed point A here. There is a fixed point A here. So then the limit of
Sir,
yes.
please don't take the point as A. AB is the
Oh, this is
interval.
A is already AB. Yeah, thank you. So what should I take? So maybe I'm going to take the interval as alpha beta. Okay, I'm going to take this. Thank you. I'm going to take this interval as alpha beta. Okay, and there is a point A line in this interval alpha beta, right? So then the limit of the function RT as t tending to A, it is going to be equal to B. It is going to be equal to B. So now, what is the definition of limit in single variable calculus?
Given any epsilon bigger than 0,
Yeah,
there exists a delta bigger than 0, such that something holds whenever something holds.
Okay, fine. So I am going to bring the same analogy here. So what it is? So I am going to call B as the limit of the function R as t tending to A if giving epsilon greater than 0, there exists some delta greater than 0. And of course, epsilon and delta, they are very small positive real numbers such that your RT, this mod of RT, this is less than epsilon whenever your this less than delta. Okay? If this condition is satisfied, then we say that this vector B is the limit of the vector value function R as t tends to D. Okay? Fine?
Yes.
Now here one thing is here. Again. Say now if I consider the components of RT as your FT, HT, and GT. Okay, so then.
Sir, FT, GT, HT.
HT, sorry. It seems that I am making a lot of mistakes today. Okay, anyway. So now, and again, if I call the fixed vector as B1, B2, B3, right? So under this definition, what is going to happen? Your if from here, what is that going to imply? Your limit, this t tends to A. So this is simply going to be limit t tends to A ft, limit t tends to A gt, and limit t tends to A h. Right? So that means if I equate it to B, so what I'm going to get, I'm going to simply have limit t tends to A, your ft equal to B1. Similarly, I mean that of GT, that is going to be equal to B2, and that of HT, that is going to be equal to B3. Right? So this is the way it works out. Okay. So now let us come to the definition of continuity. Again, I am considering some intervals alpha beta, okay, in the real line R, and I am considering a fixed point A here, okay. So then this vector value function R, it is said to be continuous at the point A if limit t tends to A RT, this is equal to simply R at A. That's limit are at A. Okay. So now I'd like to prove a theorem, or you may consider it as an exercise. Okay. And just I'm going to give you some hint. I'm going to prove only one part, and the remaining part you try at home. Okay. So what is this? This exercise is you have already done it in single variable calculus. Just what you have to do, you have to extend it to. So this is the exercise. Okay. And this was about continuity. So this is about the theorem of limit. So that limit t tends to A RT, this is equal to B, if and only if for epsilon greater than 0, there exists a number delta greater than 0 such that if 0 t minus a this, then your okay. This is basically what? This is basically the definition of limit, isn't it? Right? This is basically the definition of limit. Okay.
Yes.
So if you want to prove it, see, because it is it can only if, so it is both a necessary and sufficient condition for the existence of limit. So what is happening out here? I have to prove both ways. Okay. Okay. So now let us just yeah. So firstly, if so because this is an exercise, that is why I'm writing this answer. But in answer, I can write down the proof. Okay, fine. So firstly, let us assume that. Let us assume that your the limit exists. Limit t tends to A, RT equal to B, and let us also assume that your RT, it has the components as functions ft, gt, ht, okay, and B has, like, say, fixed components b1, b2, b2. Okay, fine. So then obviously what is going to happen from this relation, what I can do, I can find out eventually that, as I told you, limit t tends to A, ft equal to b1, limit t tends to A, gt equal to b2, and limit t tends to A, ht equal to b3. Fine. Now you see, I mean, once I have reached these three different statements, it is nothing but it defines a limit for each of those functions, right? Each of those functions at the point A, those individual functions, right? So now, if I go by the definition of limit for a function of one variable, so then from this, what it will tell me, that from here I can say that this implies giving epsilon greater than 0, there exists, I mean, positive, let me call it numbers. I'm going to call it, say, firstly, say delta 1. Say I'm going to relate delta 1 to this function. Okay, so what is that? I mean, your ft mod of ft minus b1 less than, for the timing, let me take it as epsilon. I'm going to change it later on. Epsilon, I mean, whenever delta 1 is greater than 0. Okay, so similarly for this function also I can
whenever delta 1 is bigger than 0 or something else?
No, delta 1 is a strictly it's a strictly positive number.
No, but it should be less than mod of t minus a.
Oh, yeah. Thank you. No, that has to come. Whenever, yes. Whenever, yes. Whenever this. Okay, thank you. Okay, so similarly for gt minus d1 also, I can write it as this t minus a, something like delta 2. So there it is. So basically there it is positive numbers, delta 1, delta 2, delta 3. That this is valid. This is valid. This is V2, this is V3, less than epsilon, and again T minus this delta 3. So this part you have already worked out in single variable, right? So now we are going to do some kind of mathematical manipulations. Okay. See, it doesn't matter whether you take it, I mean epsilon or epsilon by 2, epsilon by 100, whatever you take it, because you want to keep, I mean, this expression as close to 0. That's what you want. So what I'm going to do, let me simply, instead of epsilon, let me call it, okay, epsilon by 3. Okay. See, remember what we are trying to prove is that from given that the limit exists, we want to prove it that RT minus this less than epsilon whenever your 0 less than t minus a is less than this is delta, where delta is some positive number. Okay, so now if I assume that your delta is equal to your minimum of these three, delta 1, delta 2, delta 3. Okay, so then if instead of delta 1 and delta 2, delta 3, I replace it by delta, these three comments are still going to be valid. Is it okay? Fine. So
yes.
Now, if you look at this expression, and if you consider the components, if you recall, say, suppose if I consider a vector A whose components are A1, A2, A3, right? Then mode of A, that was simply this. Fine. Okay. So similarly, if you, simplify it, you will see that in order to get this expression, so this is simply going to be square root your ft minus b1 whole square, ct minus b2 whole square plus ht minus b3 whole square. Fine. If you compare that with this one, okay, it is exactly going to be like this. Fine. So now, just a minute. This one I can manipulate it like, see, suppose I consider three positive numbers, say. Suppose I write them in terms of this something like this. Fine. It is obviously less than equal to, isn't it? Because see, this should come from this, right? Because it is something like this. If A, B, C are positive, then definitely A square plus B square plus C square, this is less than equal to A square plus B square plus C square plus 2AB plus 2BC plus 2CA, and this is nothing but A plus B plus C
whole square.
Right? So that is exactly, if you follow that from here, this is going to be less than equal to your ft minus b1 plus gt minus b2 plus ht minus b3. Okay, fine. And from these three, we can see that this is going to be strictly less than epsilon by 3 plus epsilon by 3, but not always, not always. Whenever these three conditions are valid, but we can bring all these three conditions under one umbrella by simply writing 0 less than delta. Okay, and so this is equal to epsilon. So what we have proved, we have proved that your RT minus B less than epsilon whenever this happens 0 T minus A less than J. Okay, so remember this is only one part. Okay, we still need to do the only if part. So only if part I am leaving it as a homework. I'm leaving it as a homework. So what you have to do, assuming that this is less than epsilon whenever this happens, you have to prove that the limit of the function RT as t tends to A is equal to t. That is what you have to prove. And you will see that because we have already done this, you can easily prove that as well. Okay, you please try it out. So that brings me now to space curves. Okay. Space curves. Okay. See, you remember when I was considering those functions f, z, and h. Okay, I was considering them to be a function of the single variable t. I could have used some other symbol also. This could have been u, v, anything. I could have used any symbol, but there is a hidden agenda. Why specifically the symbol t is used? It is because t is generally related to time. Okay. So now let us think about a vector-valued function in this way. Okay. Say suppose I have a vector-valued function defined by ft, gt, ht, right? So that means I can relate this vector to a point P here, in three-dimensional space in such a way that its coordinates are ft, gt, ht. Okay, and you know that this OP is nothing but my vector R. Fine. So this is the way I can relate this vector-valued function R in three-dimensional space. Is it okay? Fine. So now, thank you. Now, what I'm going to do, that interval AB, in fact, generally, I'm telling you, if you want to relate it to, real life world. So that interval is generally taken as something like 0 to some number. So let me call it TF. So I am considering this interval 0 to TF, where TF is strictly greater than 0. Okay. Why it is so? Because if T denotes time here, so then what is going to happen? I am going to consider something happening from time t equal to 0 to some subsequent time, isn't it? So that is why generally it is taken as 0 and some non-negative, sorry, some positive number. Okay, the upper limit. Fine. So now let us think about this. Say, suppose I am considering the interval, say 0 to 10, 0 to 10. Okay, fine. And suppose this is 10 relates to something like 10 seconds. 10 seconds. Okay. So that means 0 to 10. So I am going to have infinite number of points here, starting from 0 and then ending at 10. So what I may do, so then corresponding to 0, I can have a point here, right? And then what I can do, these coordinates, x, y, z, I am defining through ft, gt, and xt, right? Say at t equal to 0, suppose I am, see here, I am trying to track, say, suppose a particle in space. Say. Okay, so maybe what you can think about, you are trying to track, say, an aeroplane, aeroplane flying in space. Okay, so suppose at time t equal to 0, the at t equal to 0 right now, what is the time? So it may be 11. How much? Okay, it is 11:26. Okay, so 11:26. If I consider it as t equal to 0, suppose the aircraft or an aeroplane above us, it is in Guwahati and it is moving towards, say, Delhi, right? Say, suppose, I mean, at time t equal to 0, it is in this location. And then t equal to 0.1, it is here. T equal to 0.2, it is here. Something like this. Okay. So then, if at each time, till I reach the value of 10, I track all those particles in space, I am going to have a curve. Right? Isn't it? So these kind of curve,
Yes.
it is called a space curve. So that means for all value of t lying in this interval, or here I am not using A, so I can use AB also here. But anyway, if for all values of t lying in this interval, I consider the location of a particle at different times, what is going to happen? The state of all these points in space, it is going to generate a curve C. And you will see that at each point on the curve, you can define a vector. Like this. Okay, fine. So that is the way your space curves are constructed out. Okay, so this is about space curve. Okay, so now, since by varying this t, I mean, you are trying to extract the curve C, and of course, t is a parameter, right? And that is why this curve is also called a parametric curve. Okay, so now I'll just simply show you something on the slides, but before that. So, for example, you still may be in doubt. For example, suppose I have a curve given by this. Okay, and I have been given that 2, 5. Okay, so now if you consider 3-dimensional space x, y, j. Okay, now at time t equal to 0, if I want to find out the location of a particle, you have to simply plug in t equal to 0 here, right? So the very first point will be defined by this vector of 0, 1, 0, 0, right? So my first point is going to be somewhere here, right? Next, at some subsequent time, so when your theta equal to 45, so what I'm going to get? I'm going to get 1 by root 2, pi by 4, something like this. Okay, so this one is going to be at some height pi by 4 above the xy plane, right? And this point is going to have coordinates. Are you getting my point? So now, if you look at the first two coordinates, that is cos t and sin t, right? Cos t and sin t. So what is that? So basically, if I don't consider the third component, that is going to denote what? Cos square theta plus sin square theta equal to 1. So x square plus y square equal to 1. So basically, that is going to define
A circle
of radius 1. So what we are going to get here, this is in fact going to give me a curve like this. Okay. What I'm going to do, I'm going to exactly show you that in MATLAB. See? Okay. Say, suppose I am defining, see this t equal to least space 0 to pi. So this is the interval that I have defined. Fine. Okay. So now, if I want to find out the curve in space, so I'm just simply plotting it. So see, it is something like this. Is it okay? Fine. Now, what is the role of that interval? So suppose now I change the interval to something like say 8 pi. Okay. Again, try to draw the curve. Now you will see that it has traveled more on the space. Is it clear?
Yes.
Yes. So I maybe okay. Anyway, fine. So this is the way you can construct space. Okay, fine. So now let me just go to some. So first, this I have already explained to you. Okay. And see, if you look at this expression, RT is equal to 1 plus t, comma 2 plus 5t minus 1 plus 6t. So, I mean, what does it remind you? If you look at this expression, does it have a specific form that we learned yesterday?
Straight line.
Exactly. If you recall the equation of the straight line, I mean, it was in this form. If R is your x, y, z, so this is simply what? X equal to x naught plus bt, y equal to y naught plus bt, and z equal to z naught plus ct. So basically, this is going to denote a straight line passing through the point 1, minus 1, just 1, 2, and minus 1, right? And the straight line has direction ratios given by 1, 5, and 6. Okay, so now you will see that, yeah, so this is the straight line. Okay, now this one I have already drawn. So if you have to sketch the curve, so it is going to be something like this. See, initially at 0, I mean, when t equal to 0, it starts at this point, then it squares like this. So this is the location when your t equal to pi by 2, and you know that at pi by 2, your cos pi by 2 0, sin pi by 2 1. So this is going to be coordinate. So in that way, it's going to move up. Is it clear how you can draw a space curve? Okay. So now let me come to so now what I have done. I told you that your t is the parameter. And you have seen the role of that parameter. When in MATLAB I showed you that the interval once I have taken this, once I have taken this as 8 pi, and then you saw the extent of that curve. Once it was something like this, and then once it moved like this, right? Okay. So now let me tell you that any, three-dimensional curve, even if it is given in terms of x and y, even if it is given in x and y. Say, suppose what is happening out here. Say, suppose you are giving a space curve without using the parameter t, but still there are some ways to parameterize it. Okay, so how do we do it? I'm going to show you one example, and you will see that it's pretty straightforward how you can go about it. Okay, fine. So let us. Can you think about parameterizing this? Find a vector function that represents the curve of intersection of this cylinder x squared plus y squared equal to 1 and the plane y plus z equal to 2. So obviously, see, so this is a cylinder. So can you tell me, if the cylinder is cut by a plane parallel to xy plane, then what is going to happen? We are going to get what?
Circle.
Yeah, we are going to get a circle. Of radius 1. Simply a circle. Yeah. So now, here, because the plane is different, obviously it is going to give me some other curve. So you can see from this that, see, it is going to have an ellipse. So I'm going to get an ellipse like this. Okay, fine. So then how can you parameterize it? See, the very first equation of the cylinder, it has given you a clue. Right here, if I use the parameter t, x squared plus y squared equal to 1, simply can be parameterized by what? X equal to cos t and y equal to sin t. Is it okay?
Yes.
Yeah. So that means j I can get from this equation. So basically, what I can do is x squared plus y squared equal to 1 and your y plus z equal to 2, y plus z equal to 2. These can be parameterized. So r, I can write it as cos t, sin t, and then j equal to, because y is sin t, 2 minus sin t. Okay, fine. Am I still on?
Yes.
Okay, because generally around this time, the link is lost. Just let me check. Yeah, I should be fine. Okay. So now, again, let me have a close look at this. What is missing from here? I have parameterized it, but something I still haven't told. What is that? Can you tell me? I still haven't told.
The question.
See here, what I have done, I have parameterized this curve given by this one. Okay, I have introduced the parameter t, and I told you that it can be parameterized by this. But still, some information is missing. Can you tell me what that information is? I still haven't told anything about where t belongs to. Okay, so I can take it as any interval, say 0 to 2 pi, 0 to 2 pi, 0 to 4 pi, even say some pi by 4 to pi, whatever you want to say. So let me come back to MATLAB again and let me try to work that out. Okay, say again, let me set the uh, range of this is it. And now this is my parametrization. Cos t sin t 2 minus sin t. So then you see that yeah, I'm going to get a an image value. So you may see that the orientation of the ellipse is different, but I can make the orientation the way I want. So let's see, this is like yeah. So they are going to show like these something. So this is x-axis, this is y-axis, this is z-axis. Okay, fine. And again, if I do the trick here, like say, suppose instead of making it 0 to pi, I make it pi by 2. Pi by 2. So then you can see that I'm not getting a closed curve. So in order to get closed curve, I mean at least you should take from 0 to 2 pi. Okay. And if you take and the upper limit more than 2 pi, then again it is going to repeat the same cycle. Okay, so this is the way I mean we can get space curve. So now let me come to the concept of derivative, and after that I am going to finish today's class. So just let me shake off the dust from my eraser. Okay, so now I come to a very important concept, that derivative of a vector function. Okay, and it will be easier for me if I interpret the vector function in terms of space curves. Okay, fine. See, what I'm going to do is, firstly, I'm going to define the derivative, and after that, I'm going to give you a pictorial interpretation or geometrical interpretation. Okay. Suppose, I mean, I am considering a vector value function RT, and again, t belongs to some interval, say AB. Okay. So then, the derivative of RT, I mean denoted by dRdt, it is nothing but the limit of this as h tends to 0 if this limit exists. Okay, so then we say that the derivative of the vector function R exists and it is defined as this. Okay, fine. So how do we interpret it geometrically? Say, suppose I am considering a space curve. Suppose I am considering a space curve like this. Okay, and suppose at time t, this is the location of the particle. Okay, and then at time t, let me call it t plus delta t. At time t plus delta t, the location of the particle is somewhere here, so q. Okay, so that means if I draw this vector, this is going to be my simply r t, right? And this is simply going to be r t plus delta t. Is it okay? Fine. So then this vector, it is nothing but your r t plus delta t minus rt. So far so good, right? It's clear. Okay?
Yes.
So now the first picture, let me call it the secant approach. Okay, fine. So now let me now look at this. This is nothing but this vector. Okay. Now, if I divide this vector by h, generally h is a very small quantity, or if I divide it by delta t is a very small quantity, isn't it? Fine. So then that means 1 by delta t, it is going to be a very big number, right? So basically, you have a vector pq. So pq was nothing but the vector rt plus delta t minus rt, right? Now you are multiplying it by a scalar, which is nothing but 1 by delta t, which is nothing but 1 by delta t. It's a big number. So definitely the new vector given by this, it is going to be along the same direction of PQ, but its length is going to be much bigger than that. Is it clear?
Yes.
Isn't it? So what I am going to have, I am going to have some vector like this. In fact, this vector, say this one was this, and this whole big vector is this quantity. Is it okay? So now you can see that if I consider this part, say suppose this is T, this is Q, okay? So obviously, if this is R and of course RT, and this is RT plus delta T, and see this vector passing through P and Q, it is called the secant vector. Okay? So now when you let delta T tends to 0, okay? See, now suppose I am considering, say this delta T, if I make it smaller, say, then what is going to happen? I mean, say earlier it was at this location. Sorry. Earlier it would be at this location, isn't it? Before reaching the point Q, right? The particle was at this point, isn't it? Right? So then my secant vector would have been something like this, isn't it? Now, if you go on reducing delta T, okay, let me try to say suppose delta T equal to say 0.05, okay, and say suppose T was equal to 10, right? So then at T equal to 10, the particle was here. At delta T equal to 0.05, it was here. When delta T equal to say 0.03, say, it would have been here somewhere, isn't it? Because the particle is moving like this along this curve. Is it okay?
Yes.
Okay. So then, even before that, it would have been here. So then your secant would have been something like this, secant vector, right? Exactly when it is almost, when delta T is almost equal to 0, then what is going to happen? This secant, it is going to be exactly tangent, right? It is going to be touching the curve at the point P. So that is why. So this is the geometrical interpretation of the derivative of the vector function. Okay. So that means, and again, dr/dt, it is also denoted by r prime t, right? And if r prime t is not equal to, say this 0 is a factor. If not equal to 0, so then this derivative defines a tangent to the curve C, at the point P. Okay, fine. So this is the geometrical interpretation of the derivative of a vector function. Okay, so now, say I have already told you that this tangent vector, if I denote it by T, this is my tangent. This is my tangent. the derivative unit tangent. So if you have to find a unit tangent, then it is divided by t cap. So this is simply t divided by absolute value of t. So this is simply r prime t and mod of r prime t. That's okay. So in my next class, I'm going to elaborate a little bit more on that, little bit more about that. And what I'm going to do in my next class, I'm going to do argument as well. Okay, thank you.